Welcome to electronics. I've got my whiteboard. We also have, you can hear me on the microphone, hopefully. We've got schedule that I can show up here. There's our syllabus. This is all going to change from year to year, so I'm not going to go through it too much with you. I have to do that on the first day of class anyways. So welcome to electronics. This is my experiment. This is a method I'm going to use to teach. We'll see how this goes for you and for me. This is going to be our first class. I'm not going to go into too much detail on how we're going to use all of this here, but hopefully this works pretty well. Wanted to show you the books. I've got two different versions of the same thing. Sadra Smith Microelectronics. This is 7th edition. This is 8th edition. 7th edition is what I'm going to be primarily pulling out of. There's not much difference between them for this class. You can get either one. Obviously, the 8th edition is going to be a lot more expensive. And it is an expensive book. It's also a thick book. It's a great book. Just wanted to point out, you can kind of see this on here. We only use the first third. You can see the color change right there. And over here, there's no fingers or anything at all. So we only teach for this semester out of this first third of this book, and so that's going to be the important section of this book that we're going to cover. And so you're paying for a lot more book than you're ever going to use, but it is what they consider the Bible of electronics, and everyone who knows electronics goes back to Sadra Smith, so it's a very classic text. Now we can also do stuff in MATLAB, and we're just going to start off. The direction that I go on this is I actually start in chapter 4. So I'll just show you that really quickly at the beginning. What the layout is. They start at amplifiers, okay? And so this is we're only going to be doing section 1 or the part 1. If we look at part 1, I go in a weird order. I'm going to start off with diodes, okay? And then we're going to jump back and do semiconductors. Okay, and then we're going to jump back even further and do amplifiers and operational amplifiers. Okay, and hopefully you have some background in operational amplifiers, but then we're going to jump forward all the way to BJTs, and then if we have time at the end of the semester, we jump back to chapter 5. So it's a weird order on this, but I do this so that we can get into the labs in proper time. And so let's just do some basic stuff here. If I have some sort of, and let's just make this an arbitrary signal, I'm just going to call it V of t. We just make a simple R1, R2 voltage divider. This should be pretty familiar. Let's get our brains back into this mode of looking at this. I'm going to call this V2 of t, and this one here, V1 of t. And so we have to do some notation on this as well. But let's just take a really quick look at this right now. If we know how to do this. This is all math based. We have an equation for a voltage divider that says V2 of t is going to equal R2 over R1 plus R2 times V of t, our source that came in. And we can do the same thing for V1 of t. And that's because this is all these components are linear. There's no strange math that we have to do with these particular components. There's nothing nonlinear. There are no discontinuities. We can take voltage negative, positive, and nothing really changes. And so let's just take a pause here really quickly. I'm going to introduce something, and I might have to do a separate video on this. But let's do this with the V. There's capital V, there's little v, and then we can also look at the subscript. So I'll just say this is V sub D and V sub D, and there's also a little v sub D. And this is completely annoying and confusing. This we're going to say is the large signal. So this is how the book does it. And so large signal might not make sense to you, but you can consider it static or DC. This is things. This is the DC. V, little v, we're going to call the small signal. Okay. And you could say this is the AC with no DC. So there's DC. Okay, nothing. This is the combined. V, it's a small with a large subscript. It's kind of weird that this is going to be V sub D plus V sub little d. Okay? And this doesn't make quite sense yet, but let me give you an example of this with a signal. So here's our time, here's our volts, that we'll put up here, and we have, and let's just put a little waveform like this. Okay? So looking at it like this signal here would be little v big D of t. Okay? Now let's give some equation to this. Little v big D sub t is equal to, and let's put this up here, 3 volts is equal to 3 plus 0.25, and that looks like a sine wave to me. Yeah, that looks like a sine wave to me. Sine of 30t. Okay? Make sure that doesn't look like it's confusing. That's our time domain on it. Okay, so what does that mean to you? That means this portion here is VD. There's a Bob Hope. This is V little v. Okay, and this seems a little confusing that we're separating them off, but we have to consider AC separate from DC. And so this is how we're going to try to differentiate between the three. There is no such thing as capital V little v. That doesn't work, but this works for everything. So if we do currents, we have I and little I, and then we have the subscripts that go with them. This gets confusing if we have a subscript like S, because we can't tell the difference between big and little. So that doesn't help us. So this is a convention that we're using for this. And the book uses the same convention. And so you're going to have to get used to these new terms: large signal, small signal. And it's going to be something that's going to be new. Okay? So let's get back to nonlinear elements. We're going to ignore small signal, large signal, but we're going to still use those values. And so, okay, resistor, plus, minus, voltage, okay, current going through. Let's do all, we're just going to do all this stuff here, okay. Okay, we have a voltage on there. We know that V of t is equal to I of t times R, okay. Straight, linear, mathematical. We're going to introduce a new component. Looks like a triangle. We call this side the anode. We call this side the cathode, spelled with a C, but we use K as the notation because C is already used for our friend, the capacitor. We don't want to get confused. This gets even more confusing down the road because we have another friend here that's a BJT, and it's going to have a collector, an emitter, and a base. And that just screws up the C thing altogether. So just ignore that for right now. Just know that whenever you see a K and an A, those two together are going to denote that we have a diode that's in our midst. Okay? And there are lots of different diodes out there. You should be familiar with whole bunches of them. Let's see. So we can do the same thing. I'm just going to do V, and I'm just going to do large. I'm going to do combined signal. So VD of T, and let's just say current, IV of T. What's the relationship? For resistor, we had this relationship. This one has a nonlinear relationship, okay? It's a one-way valve. It only allows current to flow from the anode to the cathode, positive current from the anode to the cathode. In other words, current may only flow this way. It acts one of two ways. And so we're also going to be talking about ideal. Okay, the ideal diode. Okay, the ideal diode means it's perfect, and and there's no such thing as perfect in this world, but in theory land, it will act that way. So ideal diode means that when we go, that this is going to act one of two ways. So there to there, those are two different ways. It's going to look like an open or a short from anode to cathode. And what determines that is if you're trying to push current through it or not. Okay, so if we're trying to push current this way, if you try to push electrons electrons the opposite way. If you're trying to push electrons this way, it'll act like a short. If you try to push electrons, no electrons will flow. But if you try to push current this way, sorry, electrons flow opposite of current, you know that. But if we try to push current this way, it will open up. And this may not seem very useful at current time, but this opened up the world of possibilities. Linear mathematical solutions can only get us so far in the world. And there's lots of examples of why this is important for us. We can start to make logic gates with diodes, for example. But it looks like this, and so it's really kind of a funny relationship, because as we go back and as we look at our diode, okay, and let's put it in a circuit. It's best never to have a diode by itself. Let's always put it with a friend. Okay, and so we're just going to put, let's just put 5 volts for there now. This will be 5 ohms. We'll do some simple math, and then we have our diode here. And the question is, what's the voltage of our resistor? Notice I'm doing all large case. And what's the voltage of our diode? What do those look like? Well, we have to ask the question. So what we need to do is we can't treat the diode. We don't know what state it is in, and we call that forward biased or reverse biased. Force and forward bias is if it has current flowing through it, looks like a short. Reverse bias is when it looks like an open, or trying to push current the wrong way. And it's probably pretty obvious to most of you by now that if we try to push current this way, that it will indeed flow. This will behave, the diode will behave like a short. This will equal 0, and this will equal 5. The other thing that we're interested in is we would like to know how much current there. In this case, it's going to be 1 amp. That's a honking powerful resistor. In this case, would be equal to 1 amp. And the way that we got, but how did we get there if we didn't know? So if we did a more complex circuit, it may be obvious. So I'm just going to put this here, and we have to try both of them and see which one works. Okay? So in forward bias, the current is going to be positive. In reverse bias, the voltage, positive current. In reverse bias, voltage will be negative. Okay? So if we go through and if we were to do this test and we found out the current through it were negative from the anode to the cathode, then we'd have to say that is not true. We'd have to go and do the test and make sure that we had a negative voltage over that. So let's do kind of the dumb thing right now, and we already know that that other one is the case, but we're going to test this as if it's an open. So we have to do one of the 2 possible combinations. There are 2 possible combinations which could be right. This is binary for the diode. It's either forward bias or reverse bias. And so as we look at this, now we're going to do it here, and we're going to look and see if my voltage from A to K from the VD is going to be negative. As we look at this, what's our current? In this particular case, it's the current would be 0. Okay, voltage over the resistor would be 0, and that means that our voltage of our diode would have to be 5 volts. As we do KVL going around the loop, we know that this voltage here. And so that would be, this is not true. All of this is false. We'd go back and we'd retry it with a short there and a 5 ohm resistor, and we get back to exactly where we were at. Normally here, 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 and then we would check. We would check if we have positive current. We'd say, yes, that's true. So there's a very first example. Let's do another one. Doesn't matter which side the resistor goes on. Not much. It can, but not in this simple. So we'll just do this. This is a diode. So it looks very much the same as we did before. Oops. VR1. And let's put a 5 ohm resistor there again. Okay. And as you look at this now, we need to go through the test. And so we're first going to treat the diode like a short. Okay. So what happens when we put the diode in as a short? We're going to go through and say if it is indeed forward biased, then we're going to go through and figure out what the voltage and the current is. And we come out and we look at the current. This current would be equal to negative 10 over 5 ohms, and we get negative 2 amps. And we would go and we'd say the current, is the current positive? Forward bias, positive current. And the answer is no, that's not true. And so we can't assume that. We go back and we test the other way. We test it this way. We look at this, and now the voltage from V to D is going to be negative 10, and I'm just doing that by inspection. So you can come through here and you can realize that we rise up negative 10, then we have to drop by negative 10. Thus, the voltage drop from here to here, from positive to negative, is in negative 10. Okay, so this is reverse bias. We know that ID is equal to 0, and we know that VD is equal to negative 10. So we're going to pause it right there. This is a good start for our video, and I'm going to keep on making a few more. Let's just keep them short like this.